the problem. In the PDF I posted for you on Blackboard, you have the main equation summarized at the beginning of the chapter, and which we have developed together today. And then we will start to do problems together. So for problem one, a machinability rating is to be determined for a new work material using the cutting speed for a 60-minute tool life as the basis of comparison. So if you remember in the course material also, we talked about the machinability rating MR, which is if you want just to compare materials in terms of machinability. So one method to compare materials, okay, is to take a base material to determine the cutting speed, let's say for this base material, okay, and then we will divide the cutting speed for another material by the cutting speed for the base material to assess the machinability rate, okay. So we can compare if it's a better tool or not in this case. So let us see an example here. So for the base material, test data resulted in Taylor equation parameter values of N and C, where the speed is in meter per minute and the tool life is in minutes. For the new material, the parameter values were N equals 0.21 and C equals to 400. So in general, the criteria will be to compare, okay, for a certain, for same lifetime of the tool. Let's say here, for example, for 60 minutes, okay. So for a tool life of 60 minutes, well, what will be the cutting speed, the maximum cutting speed before, we can consider that we cannot use it anymore. So of course, the better your material is, the higher will be the speed when the maximum speed we can reach. Okay. So here, for example, we can calculate for the first material, which is the base material. They gave us the parameters N and C. Okay, N and C for a tool life of 60 minutes. Okay, so we are operating to find the cutting speed of operation for this lifetime. We will use the Taylor equation. Okay, so we have that V times T to the power N is equal to the constant. We have that for this material, they gave us that N and C are respectively 0.29 and 500. So we can replace, we can say that V corresponding for a tool lifetime of 60 will be equal to C over T to the power N. And C here is 500 for the base material over the tool life, which is 60 minutes, times to the power N, which is 0.29. So in this way, we can calculate what is the cutting speed of this base material, which will correspond to a lifetime of 60 minutes. Okay. Now, if you want to compare materials, you can take a certain reference. Okay. Here, what is little bit subjective here is the selection of reference. You can select any reference, and but once you select the reference, you can compare several materials based on it. Okay. So for example, if I tell you now, I want to compare, okay, this base material with a new material. For the new material, okay, we have that for the same lifetime, which is 60 minutes, the values of C and N are 0.21 and 400. This will allow me to calculate what is the cutting speed for the new material corresponding to this lifetime. And of course, higher is the cutting speed, better will be the material. This is why we can assess the machinability rating as the ratio between the cutting speed for a certain tool lifetime over the cutting speed for the base material for the same lifetime, of course. And here, for example, we selected 60 minutes tool life, and we calculated the corresponding value of N and C for the two materials. And based on this, we can say that the new material is better than the base material because the speed it can reach for this lifetime, okay, is higher. So, for example, here the machinability rate is 111%. Now, just to see that this is the machinability rate, if you want, will tell me, it will allow me to compare different materials, but it's not, if you want, the value of the MR will not be constant. It will depend on the tool life. And for example, if you take the same two materials, but now you decide to compare based on a lifetime of 10 minutes, you will still obtain, the comparison will be different. Okay, and the machinability rate will be is a subjective estimation because it depends on the value of, if you want, the tool life that you are investigating. So for different tool lives, the comparison between materials will not be the same. Okay, so we should just pay attention for this. So when we perform any comparison, we should provide the tool life. Okay, because depending on your application, and if your application requires very large tool lifetime, then you will consider the following comparison based on 60 minutes, let's say. While if you are interested in operations of tool lifetime of 10 minutes, then the comparison will be different because as you can see here, in the case of 10 minutes, the new material is worse than the base material. While for 60-minute tool life, the new material is better than the base material. So this is to tell you that for different test conditions, we often come up with different machinability results. Okay? So always we should specify the conditions of testing in order to compare the materials together. Another problem, a part to be turned in an engine lathe must have a surface finish of 1.5 micrometers. So when they tell you it must have this surface finish, this represents what? This is the actual roughness. Okay, so the surface finish of the product is, if you want, the value of the roughness that we have. Okay, now the part, this is the actual roughness that is desired. This is our actual, equal to 1.5 micrometers. Now, the part is made of an aluminum. The cutting speed is 1.5 meter per second, so this is V. Now, concerning the type, it's important for us to get what, if you remember, we said that always the actual roughness is different than the theoretical one. So we need the graph. We need to know what is the type of material used in order to use the corresponding graph, the corresponding curve on the graph. Okay. So we have that the cutting speed is 1.5. The feed is also given. We have the value of feed is 3 millimeter. This is the depth. So here we have the depth is D equal to 3 millimeter. We want to find the feed. Okay, D is 3 millimeters. The nose radius is given to be 1. Determine the feed required to achieve the specified surface finish. Okay, so first let us write the equation that will involve these parameters. First, we know that aluminum is a ductile material. Okay, so for the cutting speed given, which is 1.5 meter per second, if I go back to the graph we have seen in the course material now, we can find that since it's a ductile material, so I will look at this curve. Okay, and the speed is 1.5 meter per second, and since here the speed is provided in, so if you look at the scale here, you have in meter per minute. So you should convert from meter per second to meter per minute. You have a cutting speed of 1.5 meters per second. Okay. Just guys, do you see that it's recorded? محطوط عندكم إنه that it's recording because I cannot see it.
Yeah, doctor.
Okay. So it's 1.5 times 60. So we have 90 meters per minute. Okay. So the cutting speed is 90 meters per minute. Therefore, now I can use my graph. I take 90, so for cutting speed 90, and I go to the corresponding graph, which is for ductile material. This is the graph of ductile material. Then I read now the corresponding value of the ratio. The ratio is 1.25. So knowing the actual roughness and knowing the ratio, I can assess what is the theoretical value of my roughness. Okay, so now using this formula, I can say that our theoretical is our actual over the ratio we got from the graph. So it's 1.5 micrometers over 1.25. So the theoretical roughness is 1.2 micrometers. Why we need to get it? Because we have a relation between the theoretical roughness, the feed rate, and the nose radius. Okay. Here in this problem, they gave us the nose radius. It's given. Okay, it's equal to 1 millimeter. The RI was calculated, so the only unknown is the feed rate. Now, please just pay attention for units. Okay, so if you use, let's say, the nose radius in meter and the roughness in meter, then you will get your feed rate in meter. Okay, so you should have a certain agreement between units. So if f square is in meter square and the nose radius is in meter, Ri will be in meter. So use same units for all parameters. Okay, this is why you should convert. So here the nose radius is given in millimeter. It's 1 millimeter. So multiply. Make sure to multiply by 10 minus 3 to get it in meter. And for the feed rate, also we should apply. The feed rate is to be calculated. Okay, for the roughness, we've calculated in micrometers. So to convert to meter, we should multiply by 10 to the power minus 6. Okay, now the resulting unit of the feed rate will be in meters. And you can then after convert it to the unit you want. So you can express it here in millimeter, for example. Okay. And always the feed rate, okay, here we have a turning operation, so it represents the millimeter per revolution, and for each revolution, how much we are advancing, okay? Now, they also, so this was the question, we want to calculate the value of f. So we are done with this problem, okay? Just please pay attention. Sometimes they give you some given just as tricks. And here, for example, we didn't need the depths. So they gave us the depths of code, but we didn't need it in the calculation. So and many times in the given, you will have information that is not required. So just you should know which information to select to solve your problem, okay? Any question on this? So hopefully next time we will be done with this chapter, and we will be done with the program. Okay. Just I posted for you chapter 25, 26 just for your own information, but because the time, yani, I don't want to stress you a lot. Yani, this chapter is very long, so it will not be included for the final. But for your own information, I posted it on Blackboard. Okay.
Okay, doctor. Yes, doctor, can I speak to you in private بس نخلص?
Yes, sure. So any other question before we start? Okay, yeah, let's see you next time.